Everything you see, everything you touch, even the air you're breathing right now, it's all made of atoms. Think of them as the ultimate, tiniest Lego bricks of the universe. They are incredibly small, yet they build everything from a grain of sand to the most distant star. In the very heart of each atom is a dense core we call the nucleus. This nucleus is a bustling place, packed with particles called protons, neutrons. Each proton carries a tiny positive electrical charge, which we can think of as a positive one. It's the positive center that gives the atom its identity. Zipping around this central nucleus are even smaller, lighter particles called electrons. Electrons are constantly in motion, occupying specific regions we call electron shells energy levels. Unlike the protons in the nucleus, each electron carries a negative electrical charge, a -1 charge. Imagine the electron shells as floors in a very exclusive apartment building. Each floor has a strict limit on how many residents or electrons it can hold. These rules are non-negotiable in the world of quantum mechanics. First floor can only hold a maximum of 2 electrons. Once that floor is full, extras move up to the next level. Second floor can accommodate up to 8 electrons. Third floor, for our purposes, also holds up to 8 electrons. This orderly arrangement governs an atom's behavior. The atomic number, the number of protons, defines the element. Any atom with 6 protons is carbon. Any atom with 17 protons is chlorine. A neutral atom must have balanced charge, so atomic number also gives electron count. Neutral chlorine, 17 protons, therefore 17 electrons. Electron arrangement for chlorine, 2 in the first shell, 8 in the second shell, 7 in the outermost, third shell. Now sodium, atomic number 11. 11 protons, 11 electrons. First shell takes 2 electrons. In the world of atoms, the ultimate goal is stability. It's like wanting to be comfortable and relaxed. For an atom, this state of ultimate stability is achieved when its outermost electron shell is completely full. Think of it as a sense of completeness. When that outer shell has its maximum number of electrons, the atom is energetically content and doesn't feel the need to interact with other atoms. It's happy just the way it is. This is the golden rule of chemical reactivity. A full outer shell equals a stable atom. There's a group of elements on the periodic table that have naturally achieved this state of perfection, the noble gases. Elements like helium, neon, and argon are the VIPs of the atomic world. Helium has a full first shell with 2 electrons. Neon has a full outer second shell with 8 electrons. Argon has a full outer third shell with 8 electrons. Because their outermost shells are already packed to capacity, they are incredibly unreactive. They don't need to gain electrons. They don't need to lose electrons. They don't need to share electrons, so they tend to exist as solitary stable atoms, rarely forming compounds. But what about all the other elements? Most atoms do not have full outer shells. Sodium with its 1 outer electron, chlorine with its 7, they are unstable or reactive. Let's see this in action with our friends, sodium and chlorine. A sodium atom, as we know, has 11 electrons arranged 2-8-1. It has 1 lonely electron in its third shell. To become stable, it has a choice. It could try to find and gain 7 more electrons to fill this shell, which is very difficult. Or it could take a much easier route. Simply lose that 1 outer electron. If it jettisons that single electron, its third shell disappears, and the now outermost second shell, already full with 8 electrons, is exposed. Bingo! Stability achieved. When the neutral sodium atom loses that 1 negative electron, the balance of charge is upset. It still has 11 positive protons in the nucleus, but now only 10 negative electrons. With 11 pluses and 10 minuses, the atom now has an overall charge of +1. It is no longer neutral, it has become a positive ion, Na+. This sodium ion is far more stable because it has a full outer shell. The atom achieved its goal by giving an electron away. Now, let's look at chlorine. A neutral chlorine atom has 17 electrons, arranged 2-8-7. Its outer shell has 7 electrons. It's so close to full, ding! It just needs 1 more electron to reach 8. For chlorine, gaining 1 electron is much easier than losing 7. So, if a sodium atom nearby wants to get rid of an electron, the chlorine atom is happy to take it. A perfect chemical match. When chlorine gains that extra electron, its charge balance changes. It still has 17 positive protons but now has 18 negative electrons. With 17 pluses and 18 minuses, it has an overall charge of -1. it becomes a negative ion, Cl-. Like Na+, Cl is now more stable with a full outer shell. By gaining an electron, it reached stability. The positive Na+ and negative Cl- are strongly attracted, they form an ionic bond.